Hello, welcome to the second of a series of tutorials for PRISMS-PF, an open source phase field modeling framework developed at the PRISM Center of the University of Michigan. In this video, I will show you how to set up and run a simulation for explicit nucleation and growth in PRISMS-PF. Specifically, we will simulate the growth or shrinking of a circular seed of size close to its critical size. Before we begin, I should mention that for the sake of saving time, I will skip some of the details on how to compile and run the code. So I encourage you to watch our previous PRISMS-PF video on installation, running, and results visualization. For this tutorial, we will guide you through the necessary steps of creating a new application, and then in this application setting up the governing equations, the model, the simulation parameters, and the initial and boundary conditions. Again, I will include a set of useful links and resources in the description of the video. Okay, we are going to start with a bit of background, specifically on classical nucleation theory, and then a brief description of the model, including relating the free energy parameters to the properties of a nucleus of critical size. We will then present the governing equations of the model, and then show the time discretization of the equations and the weak form, which is how equations need to be input into the application. After that, I will go through the implementation of the model, including setting the parameters, equations, and initial conditions. And finally, I will demonstrate once more how to run the code and visualize the results, including generating a moving visit. Okay, let's go through a brief overview of classical nucleation theory. This theory predicts the rate of nucleation of a stable phase starting from a metastable phase. The rate is given by J, this expression right here, which is proportional to the number of nucleation sites, that is N. The rate at which molecules or atoms attach to the nucleus, that is beta star, and the Zeldovich factor Z, which I will come back to in a bit. But most importantly, J has an exponential dependence on the inverse of temperature and on this quantity delta G star. In general, delta G is the change in Gibbs free energy associated with the spontaneous creation of a nucleus of a certain size, and it has two contributions. A volumetric or bulk contribution, which is always negative, and a surface contribution, which is always positive. So there are two contributions that are competing. So the plot of delta G versus nucleus size always looks like the plot on the right. For small sizes, the surface term always wins, and for large sizes, the volumetric term takes over. So consider, for example, that a nucleus is formed via spontaneous fluctuation. Now there is a minimum size that a nucleus must have in order to keep growing, and that size is precisely given by the maximum of the energy of this curve. This maximum of energy, which is sometimes called nucleation barrier, is the delta G star in the equation. And the corresponding R star in the plot is called the critical radius of the nucleus. So finally, back to the Zeldovich factor Z, this gives the probability that the nucleus at the top of the barrier will go on to form a new phase rather than dissolve. Before I forget, I just want to mention that for the sake of time, in this video I'm not going to go through the derivation of equations, but there are many resources where you can learn about classical nucleation theory and nucleation in general, such as this book I took the figure from by Porter, Easterling, and Sharif. Continuing with classical nucleation theory, you can actually show that the critical radius and energy barrier are given by these expressions here, on the left for 2 dimensions and on the right for 3 dimensions. What's important here is that these expressions depend on sigma, which is the interface energy density, sometimes called interfacial energy, and on delta G, lowercase g in this case, which is the difference in bulk energy density between the metastable and stable phases. We will come back to these expressions in a bit after we discuss the phase field model, and I will actually show you how to relate these quantities to the parameters of the model. Okay, so I already talked about this particular phase field model on a previous video, but let's go over it again. We start with a free energy which has a bulk and a gradient energy contributions, and we are using the symbol phi as the order parameter here. This order parameter can represent different physical properties depending on the model. Here, for example, we define it as a rescale concentration of one of the components in a 2-component system. And we will also assume that each of the values of phi at the 2 minima of the double well represent the rescale coexistence compositions of 2 different phases in equilibrium. Also, since phi represents a concentration, we will have to use conserved dynamics, but we will talk about that later. So back to nucleation, let's consider a scenario in which we start with a homogeneous metastable phase with a concentration phi naught. And this phase will give rise to a small nucleus of a new phase with composition phi sub n. It can be shown that for this transition, the energy barrier and critical radius for the nucleus are given by the expressions below. These expressions are very similar to the ones we showed a couple of slides ago, except we are now using Helmholtz free energy, which is F, and grand potential density, which is omega, because we are considering nucleation that occurs in a system with a constant volume and also constant average concentration. And now, from phase field, we have a free energy expression that can account for bulk and surface contributions. So we can calculate delta omega and sigma from that energy. For delta omega, we can just calculate it using the bulk part of the free energy. And the resulting expression is the one enclosed in the red box. But we also need to know the value of phi n, which, if you remember, it is the composition of the nucleus. And that composition can be calculated using the equation at the bottom, which states that the chemical potential of the original phase and that of the nucleus should be the same. And for sigma, we can derive an expression by obtaining the surface energy density for an interface in equilibrium between the coexistence alpha and beta phases. For this, we consider the equilibrium planar interface in one dimension between the two phases, which is given by this expression that contains the hyperbolic function. So if we calculate the energy of this interface per unit area, or per unit length if we are in a 2D system, we can get an expression for sigma. So now we have a way to relate the energy barrier and the critical radius of a nucleus to the free energy parameters of the phase field model. And at the end of this video, we will go through two simulation examples that will hopefully illustrate this relationship. One in which we evolve a single nucleus that is originally slightly larger than the critical size, and another one where the nucleus is slightly smaller than the critical size. But first, let's review the dynamics, which will describe the evolution of the system after we've placed the nucleus. So, since we want conserved dynamics, we use the Cahn-Hilliard equation, which for convenience will be split into two coupled equations so that we do not have to calculate a fourth-order derivative. And for PRISMS-PF, we need to discretize the equations in time using the forward Euler scheme. So finally, since PRISMS-PF uses the finite element method, we will need to input the equations in the weak form. And more specifically, we will have to directly input expressions for each of these gradient and value terms for the mu and phi equations. Okay, we are almost ready to start with the implementation. But first we need to specify the field variables and the constant values that go into the model. So as you saw on the last couple of slides, we are going to solve for the variables phi and mu, but in the code we will use the letter C instead of phi. And the reason for this is that we are going to start from the PRISMS-PF Cahn-Hilliard application as a template, which uses C. And in the table below, we see the list of all the constant values that the model will need, as well as the names that we will use in the code for these variables. We have chosen this particular combination of values so that the critical radius size is approximately 1. Okay, 2 more slides. First, let me explain how we will set the initial conditions. To place a small circular nucleus in the middle of the system, we can use this expression, which will do 2 things. First, it will set the value inside the nucleus to phi n, and the value outside to a concentration phi prime that is calculated so that the average concentration of the whole system is not affected by placing the nucleus. And second, using this hyperbolic tangent function, we'll create a smoothly varying interface that is close to the planar interface solution in equilibrium. Okay, so for mu, we will simply set it to 0 everywhere, but this does not matter because mu is calculated at every step and does not depend on the previous value. Finally, we will set the no-flux boundary conditions for both mu and phi, which will guarantee that the total amount of each species within the system is conserved, so that the average concentration is a constant. And now this is the last slide before we go into the interactive part. I'm just showing the simulation parameters, system size, mesh type, the range of refinement, the element degree, and time step. Just a little information about these 2 parameters. The minimum refinement level sets the coarsest mesh in the system, and the maximum sets the finest mesh, which is usually needed at the interfaces. Okay, let's try this. The first thing we're going to do is create a new application out of the existing Cahn-Hilliard application. So let's open a Finder, Go to the directory where PRISMS-PF is installed, then go to the applications folder, copy the can-Hilliard application, and create a new application folder out of it. Let's call this application Nucleation_growth. Now we will go into the folder and edit the following files: parameters adaptive, custom_pde.h, equations.cc, postprocess.cc, and ICs and BCs. I use Atom, but you can use any text editor or IDE that you like. And let's start with parameters adaptive. This is a parsed text file where we can specify most of our simulation settings, such as the model constants, simulation parameters, the mesh settings, and simple boundary conditions. Every time we run the code, this file is read by the executable. So if we have compiled the code and need to change the settings in the file, we can just edit, save the changes, and rerun the code without having to compile. Okay, so I'm showing the slides with the settings on the left side of the screen so that we can see the new values that we need to input. We're going to start with the simulation parameters. We are changing the size of the system in the X and Y directions. And since the number of dimensions is 2, the size in the Z direction will just be ignored. Then we change the initial refine factor to 8 and the polynomial element degree to 1. Next, we change the maximum and minimum refinement levels. And we will also reset the lower and upper bounds for refinement. This may require a bit of trial and error. We want to make sure that the mesh is sufficiently refined in the interface and not too refined in the bulk. For this problem, I found that the interval from 0.025 to 1 works reasonably well. Next, let's change the time step. Okay, for the boundary conditions, they are already set to natural, which means zero derivative, so we don't have to do anything there. Next, we will add the model parameters in the model constant section. The mobility and the gradient energy coefficient are already there, but we have to first change the value of this coefficient to 0.01. And we need to add the rest of the model constants in the table. For the initial radius of the nucleus, we will choose 0.9, which is slightly smaller than the critical size. Notice that we cannot define delta here because it is calculated as an operation involving two other constants, and we cannot do operations in this file, so we will define delta somewhere else. The last thing we'll do here is set the number of time steps. We'll pick 30,000 and the number of outputs to 30, which means that the simulation will generate an output file every 1,000 time steps. Okay, we are done with the parameters file. Let's go to custom_pde.h. This file contains the class custom_pde, which is a subclass of the main class of the framework, which is called matrix-free PDE. So all the methods and variables specific to this application must be declared here. The only thing that we need to do for this application is declare all the model constants that we added in the parameters file. And we can also define delta here, and we are done. Next, let's go to equations.cc. In the first section of this file, we have a method to declare all our field variables. In this case, we do not need to change it because they have the same names. Notice that each variable has an index to identify it starting from 0. So C is the variable with index 0, and mu is the variable with index 1. And the next method is where we define expressions for the right-hand side of the explicit time-dependent equations. So in this case, we will define the expressions for C. We do not need to do anything here because the gradient and value terms are the same as in our model. The method below is where we need to write the expressions for the right-hand side of the equations for the auxiliary variable, so mu in this case. In this section, the only thing that is different in our model compared to this one is the coefficient of the derivative of the free energy with respect to C. This one, which was constant before, but now we've set it to the variable WCV. And there is also a factor of 1/4 in our expression that the previous expression did not have. And this section is where we pass the value and the gradient terms, which are these two terms. And that is all we have to do here. Let's save and go to postprocess.cc. This is where we set the expressions that are not necessary for the simulation, but that we still want the code to output. For example, the local free energy density. Again, in this file, we have a method to declare all the post-process field variables. And then, in the method below, we define the value and gradient expressions for the formulations. So once more, the only thing we need to change here is including the constant WCV and the 1/4 factor. And the last file we need to change is ICs and BCs. In this file, we need to set the initial value for all the field variables at each quadrature point in the mesh. So here, the index corresponds to the index of the variable. So if you remember, 0 corresponds to C and 1 corresponds to mu. So in this section, we have to write the initial profile for each variable. Since the initial condition is going to be very different than in the cantilevered application, let's just start from scratch. First, we are going to define some local variables. We will start with the coordinates of the center of the system, which is where we are placing our nucleus. Then the constant pi, then the area of the system, and then the concentration C prime outside the nucleus so that the average concentration of the system stays the same after we place the nucleus. We are now going to calculate a distance from each point to the center of the system, which is this variable dist. And with this distance function, we will define our hyperbolic tangent profile. And finally, rescale this hyperbolic tangent to the correct concentrations in the nucleus and the rest of the system. And with that, we conclude all the changes that we need to do. By the way, notice that the initial condition for mu, which corresponds to index equals 1, is already set to 0 everywhere. So the next step is just compiling and running. Just as a reminder from what we covered in a previous video, at this point you should have already compiled the core library with no errors. So we compile. Let's skip to the end. And to run, we will use this line. We're doing this because by default, PRISMS-PF will read from the file parameters.n. But if we choose this flag, -i, we can specify any other file, which is what we want to do in this case. Okay, we run. Again, let's skip to the end. And the results are in. Now, since we are going to modify the parameters file to use a different initial radius for the nucleus, let's save all the files in a new directory. We create the directory r_0.9 and move all the results files there. Now let's go to Visit, open the results files, create a pseudo-color plot, and visualize the evolution. This looks a little weird at the end because what you are seeing is not really that the nucleus is growing, but instead the limits of the color bar are changing dynamically. So to not see this effect, we are going to fix these limits from 0 to 1. And now we can clearly see how the nucleus shrinks and then it disappears. Now let's make a movie. We go to File, Save Movie, Simple Movie. Let's choose the MPEG format. Here we will only modify the frames per second because if we choose 10, it will only last like 3 seconds. So let's choose 5. We set the output directory. I always like to use the same directory where the files come from. And we set the movie name to whatever we want. Let's choose movie_C. Then we click continue, continue, and again continue. And now Visit is generating the movie. Let's open this movie and play it. Okay, finally, let's go back to PRISMS-PF and try a different radius size. We'll go back to parameters_adaptive and we'll change the initial radius from 0.9 to 1.1. Remember that the critical radius is very close to 1. The only other settings we will change is the number of time steps to 500,000 and the number of outputs to 50. I'm just doing this so the evolution lasts longer. So I'm not going to show you the rest, but we do the exact same thing. We run the code, load the files on visit, generate a movie, and this is what this movie looks like. So as expected, the nucleus will grow if it is larger than the critical size and shrink if it is smaller. So with that, we conclude this tutorial. As always, don't forget that in the description of the video, we posted a link to the user's manual, the GitHub repository, and also a link to register for the user forum, where you can submit your questions about the use of PRISMS-PF. Once again, thank you for watching.